So in this class, we will again look at some of the algorithmic aspects and problem representation. These are important ideas, and perhaps maybe starting from next class or the class afterwards, we will again review some of the features of C which could be beneficial for you. Okay, for the C programming language I meant. So the first thing is, in the last class, we were looking at the triplets problem, Pythagorean triplets problem, and we came up with some algorithm or approach to check whether a given number is a perfect square or not, and it so turned out that that algorithm is not efficient as we thought. And in this class, we will try to improve upon that. So before we do that, I would like to introduce you to the search problem. So in the search problem, you have a sequence of numbers: 12, -1, 30, 40, 60, no, 18, 0, 100, for example. And so the problem is given, so this is a list of numbers. How do you want, how can we store this list of numbers? We can store it in an array. Yeah. So we can store it in an array. Data structure use it to store a list of numbers is an array. We can store it. We can store this whole structure in an array. And then we are given a new element. We are given an element, some number like 35, and we are asked to check if 35 belongs to this list. 35, check if 35, the element 35 belongs to the array. Let's call this array. So this is the array A in which we have stored. We want to check if 35 is present in the array. How can we go about doing this? How do? We search, we look at A of 0, we look at A of 1, A of 2. Let's say if there are n elements in the array, we continue this process until we come to the end. So what is this algorithm? This algorithm, we are searching this whole array, one element after another element. Okay, 35, compare 35 with 12, with -1, 30, so on and so forth. In this case, when the element is not present in this array, how many comparisons are required? Array size is n. Array size is n. Array size is n. So worst case number of comparisons, worst case is the case when, in this particular case, when the element is not present, you have to go through the entire list. Worst case comparisons. Is n. What is the best case? Best case is like, for example, this instead of 12, if this element is 35, you compare 35 with the 0th element of A, and so it's a hit, and immediately you say, hey, the element 35 is present in the list. So best case number of comparisons is 1. Can we improve the worst case by any way, by any means? Is it possible for us to improve the worst case? How can we improve the worst case? Okay, binary search, binary search. So store. Can we will see. So as it is, if we don't, if the list, if there is no structure to this list, can we? Is there an algorithmic approach to improve the worst case? Yeah. So if there is no structure in the array, if the elements are ordered in some fashion, then uh, then it's not possible for us to do better than this. And some of you, like for example, this is a time I can kind of introduce you. Like for example, if you have 2 cores on your system, or I think almost all of you have 4 cores on your system, is it possible for us to divide the array into 4 parts, and each core will search for assign each core to each part, and a thread will will do this comparison. So if this is your whole array, perhaps we can divide it into 4 parts, and this is segment 1, segment 2, segment 3, segment 4. Segment 1 we can assign to core 1, and segment 2 we can assign to core 2, segment 3 we can assign to core 3, segment 4 we can assign to core 4. Array is stored consecutively. Yeah. Logically, can we do that, and how much speed up we get? Approximately 4x speed. Okay, 4 times. In the worst case also, you will get 4 times the speed up. So this is a very simple example of a parallel algorithm. This is a parallel algorithm. But in order to actually do it, you need to know a little bit of, this is the algorithm. And in order to realize this algorithm, you have to learn P-threads, or there is something also called as OpenMP. In your second year, in your 4th semester, there is a course called as Programming for Performance. In that course, you will learn about these things in more detail. Yeah, multi-threading. At least at a conceptual level, you understand how you can parallelize. That is what we do now. If you have a pack of cards which are not sorted and you are searching for something, and 4 of your friends are there, you just split the cards into 4 parts, and each of you can search in your respective pack. Very simple parallel algorithm. Great. So now we are not happy with this worst case number of comparisons n. But if this list is sorted, okay, if this list is sorted, then it is possible for us. Let me erase this. I want to do this here itself. So this is, if you transform this array into a sorted array, if you sort this array, then what do we have? So -1 is the first element, 0, and then what do we have? 18. So after 18, what do we have? 30, I guess. 30. No, I think help me out here, guys. 12. After 12, we have 18, 30, 40, 60, and 100. Awesome. Thank you. So now we have a sorted array. So now we have a sorted array. And once we have the sorted array, what can we do? So you are looking for the element 35. We are looking for the element 35. Approximately, you go and check the middle element. You check the middle element. There are 4 elements here, 3 elements here, no, 30. You can either check 30 or you can either check 18. So yeah, so let's say you check the element. This is the first comparison that we are doing. So 35 is the element that we are searching for. So now is 35 greater than 30 or less than 30? So 35 is greater than 30. So can we safely ignore the left half of this array? Yeah, so we ignore the left half of this array and we confine ourselves to the right half. And then again, if you look here, 40, 60, 100. So what do? We look for, we compare it with the second comparison. So 35 and no, within this 35 is less than 60. So you have to focus your attention on the left half of this array. And it so turns out the left half is this is the left half. There is only one element here. You compare 35 with 40, the third comparison, and then we will stop there. Are you with me here? Do you all understand? So pictorially speaking, the way we kind of start with is, so we have the element could be, the element that we are looking for, it could be present anywhere in this array. This is our initial estimate, our hypothesis that the element that we are looking for is present anywhere within this array. In this, from a of 0 to a of n minus 1, it could be present anywhere. And then what we are doing is we are checking the middle element. Okay, so we are computing the middle element n minus 1 by 2. Compare element E with this. Okay, so rather than this, I will say compare E, the element E with, yeah, compare element E with A of n minus 1 by 2. And there are 3 possibilities. The first possibility is E is actually equal to the element. And the second possibility is, so there are 2 possibilities. E is less than this. The second is E is greater than this element. And the third is E equal to that. If it is equal to, then we stop the search. If E is less than, what is our improved estimate of the interval? What is the improved estimate of the interval if E is less than, if we found out that E is less than the middle element? Left side, right? Left is what? 0 to n minus 1 by 2. Yes or no? And if E is greater than, then it is n plus 1 by 2 to n minus 1. So what is an important observation? While going from here to here, what is the size of the interval? The size of the interval got reduced by half. Similarly, again here we look at the mid. Okay, so we compare the element E against the mid, and then again there are two possibilities: E is less than or E is greater than the mid, or E is equal to it. So what will be the interval here? Roughly, I am just using roughly. It will be 0 to n minus half, n minus 1 by 4, so on and so forth. You do the computation. So what is happening is, if the size of the interval is reducing by half, okay, initially the size of the interval at the root level, if you think of this as the top of the tree, which is called as a root of the tree, so the size of the interval is n, and the size of the interval went down by n by 2, and then it goes down by n by 4, so on and so forth. So finally, we stop the search when the size of the interval becomes equal to 1. So what this implies is, we will stop the search after going in the depth by log n steps. The depth of the tree is log n steps. And are we exploring the whole tree, or are we taking a particular path in the tree? This is an inverted tree. Tree actually have the root down and it grows up, but in computer science, trees grow in the opposite direction. We start with the root and we keep branching into leaves. Are we taking a particular path in the tree, or are we exploring the whole tree? We are only taking a particular path in the tree. So how many nodes will be there? This is each one of these. No, how many comparisons will be there in the particular path? Log n to base 2. Yes. The depth of the tree, and the depth of the tree is log n to the base 2. Log n is simple. No? As you keep the size of the, as you keep going down, the size of the interval keeps, let's say if you take the leftmost path, this is the first comparison, this is where second comparison happens, this is where third comparison happens. If you keep going down, the size of the interval, it keeps going down by half and half. So finally, so this is n by 2, n, the size of the interval here is n, at the next level is n by 2, at the next level is n by 4, so on and so forth. Finally, at the kth level, the size of the interval is n by 2 power k, and when n by 2 power k is equal to 1, then there is nothing more to, you cannot split, there is only one element. At that time, you stop the search, and n by 2 power k is equal to 1 implies k is equal to log n to the base 2. Are you all with me here? So we can reduce the search from n comparisons, n worst case comparisons, we can reduce to log n to the base 2. But what is the catch here? What is the catch here? That we need to put in effort. We have to pre-process the data. We have to sort the data to get to this log n to the base 2. So what is the time, how much time is required? So if the time required to sort is really a lot, like for example, you and your friends, you are looking for Joker, and if it's a one-time thing, do you want to sort the whole whatever card stack so that you get that you will be able to find the Joker? Does it make sense? No, right? So, but if you're searching again and again and again, then you want to pre-process the data so that it is the time, so that you can you will be able to uh, answer the queries, search queries. These are called as search queries much faster. Like for example, like let's say JEE marks, there are 1 lakh students, and people, you keep on searching again and again and again, right? Every time how many marks I got, you want to populate. So what happens is that's the place where you may want to sort the data so that it is easy for to search, because there's a lot of time you spend. Not lot of time, there will be lots of queries. It's not a one-time thing. So later on, maybe in the next class, you will learn that sorting requires, if you want to sort, sorting requires on an average like n log n time. So what happens is if you are asking k queries, k search queries, k search queries, the question is, if you take the sorting approach, what is the time required if there is an unsorted list, you want to sort and do binary search for k queries, what is the cost? It is n log n plus k log n. N log n plus k log. This is if you take the sorting approach, sort and then do the search. So, but if you do straight search, how many, what is the time complexity? How much time? K times n. So this is approach 1 and this is approach 2. So when is approach 1 better than approach 1 better than approach 2 if Kn is greater than n log n plus k log. Yes or no? That is, in other words, when k is greater than log n divided by n minus log n. Does this make sense? There, let's assume log to the base 2. Okay. Is this okay thing to say? That when the number of queries is greater than n log n divided by n minus log n, then we can sort. N log n is the time required to sort. We are just taking it as a given. We didn't, this part we still didn't explore why it takes n log n. We are just, I'm just like telling you, hey, you know what, in order to do sorting, we have to do n log n comparisons. Does this make sense? Is this, can you think of this as a black box? This statement here is a black box statement. We didn't explain. We didn't explain, but it's just a thing that in order to do sorting, you need to do n log n comparisons. And then if you actually think about it, so this is k is greater than log n by 1 minus log n by n. As you can see, even for smaller values of n, like n4, 5, 6, this tends to 0. This tends to 0, no? This part. So approximately we can say when k is greater than log n, where then the number of queries are greater than log n, then we can go ahead and sort the data that we have and use the binary search algorithm. Are you all good here? Does this make sense? that if k is greater than log n, we can go ahead and use sort the data and then start using binary search algorithm. Okay, so we can use binary search in base of log. You can use 2, but that's not very important. Okay, you can use base 2. It is like this, like why we kind of ignore the base 2, base E kind of things many times in computer science is, let's say you and your friend or the parallel algorithm which we discussed just before. I erased it. Okay, your friend might be able to do the search slightly faster than you because he can handle the cards in his hand better. But the advantage that he gets is only so much. Your friend and you, both of you are doing the counting or search using but your friend might be able to do slightly better than you, but it's not a big deal. It's only so much. Especially as the number of cards increase, he'll also get tired, you'll also get tired, and roughly it could be the same. But the advantage comes if he has a magical way of doing things where instead of doing n comparisons, he is able to get away with log n. Then that's a issue. But if both of you are roughly taking log n comparisons but he is slightly faster than you, it's okay. Yeah, this is machine independent. Yeah, so if you and your friend, if you think of yourselves as the machines, so it's a kind of, you want to do a machine independent analysis. The constant factors that kind of come in, you can kind of attribute it to the machine speed, for example. So we don't really care about them so much. Do you get the intuition, kind of roughly what I am trying to say? We are trying to get a big picture. Okay, the minute details we are kind of keeping them aside, so what constants, etc. Yes, runtime is machine dependent, but complexity or growth is independent. Exactly. You are all doing awesome. In the last class we were so we have this problem that we want to check if something is a triplet, and so what we did is this. Okay, so we have a H. Okay, we pick H. Okay, so H is fixed actually. Okay, we are this is, remember, this is the Pythagorean triplets problem. We fix the hypotenuse and we want to check for that hypotenuse. These are all, there is the side S1, and side S1 can go from 1 to H. So we pick a particular value of S1 and then we have K is equal to H square minus S1 square. And we want to check, the question is we compute, check if K is a perfect square. This is the problem. And one approach that we tried is, we check if 1 plus 1 times 1 is less than or equal to K, 2 times 2 is less than or equal to K, I times I is less than or equal to K. And so when you do that, so finally you may have to go, and then we say that since we started with H, we can go all the way to Now we keep doing this for I less than h. Okay, we keep iterating for I less than or equal to h. So the number of comparisons that we make is h. Okay, the number of comparisons that we make is h. Does this make sense? Are you all with me so far? That we keep doing this no, till this point. And the question is whether can we do, so there are edge comparisons. There are worst case comparisons. No, so here if we write it down in this approach, worst case comparisons is h. This is what we have, approximately h. Okay, you can say h minus 1, but let's not worry about it. And so can we do better than this? Okay, that's the question. So, but one thing we know for sure is the value of I, it lies between 1 to h. Okay. So here we can apply the same approach. So the value of I lies between, our initial estimate of the value of I is it lies between 1 to h minus 1. This is our initial estimate. If at all that square root exists, that I, so here we are looking for the I. Here we are looking for an I such that I square is equal to k. So question is find I such that I square is equal to k. That is the question. So what we do is we initially start with we check we find the midpoint here, and when we find the midpoint is maybe h plus 1 by 2. And we check if I tag, and we say I is equal to h plus 1 by 2, and we check what happens. Okay, so so set our initial estimate for I. Okay, so this is what we are doing. Set I is equal to h plus 1 by 2, and we compare I star I with compare I star I with k, and there are again, if I star I is equal to k, we are done, but there are two possibilities: I star I is less than k, or I star I is greater than k. There are two possibilities. If I star I is less than k, what will happen here? What will be the estimate? Whether did we overestimate or underestimate I? If I star I is less than k, did we have underestimated I, right? So let me do one thing. So if I star I is less than k, we have underestimated I. So what will be the new estimate for I? The new estimate for I is it belongs to the interval h plus 1 by 2 to h minus 1. Does this make sense? That if we underestimate, we will go to the right. Go right. Okay, so underestimate. We have underestimated, you go right, and going right is equivalent to this. And here if I star I is greater than k, then what is the story? We have overestimated. If there is an overestimate, what happens? So we will go to the left side. Yes or no? So we go to the left side, and going to the left is equal to 1 comma h plus 1 by 2. Does this make sense? That we start with an estimate of I, and then when we compare if it's exact, we are great. Either we underestimate or we overestimate. Okay, if we underestimate, we change our estimate, we appropriately modify our interval, and if we overestimate, we appropriately modify our interval. And then we again repeat. We will see the idea of recursion in the next class, very, very important idea. So we simply say recurse. recurs, repeat the same. If you see within this tree, this is a subtree. Within this tree, the computational structure remains the same in these trees. And when you look at this whole tree, what will be the depth of the tree? So when we are going from one level to another level, our estimate of the interval in which I lies, is it going, how much it is going down by? Yeah, then perhaps, yeah, we should we have to be careful. I'm just giving a high level picture. Okay, maybe we should, kind of put a closed, yeah, thing. So these are important, but I am not, I'm trying to give a kind of high level picture. So when we are, what is the interval size at this level? The interval size is h. At the root level, the interval size is h. What is the size of the interval at the next level? H over 2. And then what happens is, as we keep going down, the size of the interval keeps going half. So finally, we will stop at a depth k, where k is equal to log h to the base 2. That is when h by 2 power k is equal to 1, we stop. Are you all with me here? Now, do we take a particular path in the tree, or do we traverse the whole tree? So if you see, we take a particular path in the tree. And how many nodes are there in this path? How many comparison operations that we do? We do k comparison operations. That is log h to the base 2 comparisons we do. So now what happens is, instead of h comparisons, worst case, we will be able to get away with log h to the base 2 comparisons. Are you all with me here? Okay, great. So now we will, so this is the basic idea behind binary search, and you should be able to write algorithms whenever you write programs. You should use this idea while solving these problems. Very, very powerful technique. It will be useful throughout. So great. So now shall we move on to the next idea, if you are all with me on this so far? I think there are some questions. Should we also restrict I to S1? Manoj has. I want to kind of illustrate the binary search, and use Pythagorean triplets as a motivation. So any nuances, other things with respect to Pythagorean triplets itself, you may want to check. Is that all right? Because the purpose is different. Okay, so now let's work on, so in the problem set that you get in assignment 3, you may have to work with polynomials. So let's say if we have a polynomial 4x cube minus 2x square plus 10x minus 12. So the question is, how do we input this polynomial? Okay, and how do we input? Two questions. How do we input this polynomial? Second question is, how do we store? Yeah, so this is where I really, so yeah, I want you to understand that this is a mathematical problem, and 4x cube minus 2x square plus 10x minus 12, it is something which we work with. Okay, but what happens is when you are when you want to use a computer to solve, to find the roots of this polynomial or to evaluate this polynomial at a particular point, you don't need to give the input as 4 times x minus 2x square, etc. You don't need to do it. Okay, there are two ways input format one. Like for example, I can give you two ways. Input format one. Input format one is, for example, you just give the coefficients. You give 4 minus 2, 10 minus 12. This is one way of doing it. And how do you store it? What is the, how do we store? Storage structure that we use. So perhaps, so this is, so a of 0, you want to store minus 12, and a of 1, you want to store 10, a of 2, you want to store minus 2, a of 3, you want to store 4, for example. Where this 3 corresponds to the degree, in general, a of the degree, whatever term, the corresponding coefficient, you want to store maybe CD. So don't try to give input as 4x cube minus 2x square plus 10x minus 12. It doesn't make sense. You have to find an appropriate input format. And so an alternate input format for this, can you suggest an alternate input format for this? First of all, before we go to an alternate, does this make sense? Or see here, we are giving higher order terms to lower order terms, or we can give, like you can even start with, start with minus 12, 10, minus 2, 4, both are possible. Okay, so all these things, so when you are working with polynomials, please keep this in mind. You just have to input the coefficients. So now, let's look at one more. Can you now suggest one more alternate format, input format for a polynomial? Like for example, if the polynomial instead of this, let's say if the polynomial doesn't have have a linear term in it. Okay, this the polynomial is 4x. 4x. This is the polynomial. Then what happens is in the input we have to give. We can we have to give the coefficient as 0 here. So this becomes equal to 0. Vaibhav, don't do that. Okay, why do you want a user to make to enter 4x? You are just making his life more difficult. Okay, it's a good idea. I understand your what you are getting to. It's good, but an alternate approach, for example, is the storage structure could still be the same. What happened? How do I undo clear? I accidentally cleared it. Control Z. Not on Zoom. This is I'm doing on Zoom. But still I tried. Wanted to test my luck. Okay, no problem. It's fine. So yeah, so other approach is like, for example, you have again 12x cube minus 4x plus 10. An alternate approach is you give a coefficient, you give the degree and then you give the coefficient. 3, 12. So when you do this, you don't need to give in the order. Okay, and 1 minus 4, this is input format. So here this is degree. No, this is not a 2D array. The internally you may still the storage is the same. Storage. So when you have A, when you see this thing, you may just say A of 3 is equal to no, or A of 3 is equal to 12. And when you look at this, you can just say A of 0, sorry, is equal to 10. And you can represent this as A of 1 is equal to minus 4. You have to be careful if A of 2, how do you know that A of 2 doesn't have any garbage value? So in order for this to happen, you need to kind of initialize all the array elements with some weird thing which cannot possibly be a coefficient. No, you cannot initialize everything with 0 because 0 is a very normal coefficient. You may want to have some weird, very super high value like 65, something like that. Initialize. So anyway, so the point I'm trying to make is this is an alternate way of input. This is an alternate way of providing input. Oh, okay. Initialize it to 0 because if there is no coefficient, then initialize it to 0. Yeah, awesome. Good, good. That makes sense. Yeah. Thank you, thank you, thank you. Thank you, Tejas. Yeah. Yeah, initialize everything to 0 and then you only modify only those coefficients of those terms which are given as input. That's it. So these are the two input formats. Now I have a question for you. Once you have a polynomial represented in the form of an array, if I ask you, can you compute the differential of the polynomial p prime x, how do you go about doing that? Can you think of an algorithm to compute the differential of a polynomial? How will you store it? Will you store it in an array or how will you store it? Because some of these things will be useful when you solve the problems in the next problem set. How do you store a polynomial? How do you find the differential of a polynomial? All these things are important. Similarly, when you are working with systems of equations, 2x plus 3y is equal to 4, 4x plus 3z is equal to 3y is equal to minus 2. How do you enter this? How do you enter this? What is the input format for this? This is a system of equations. No, the input format. There is a storage structure. There are two things that are there. One is a storage structure. How do you store it? You may use a 2D array to store it. Okay, but how do you store it? But how do you input it? The input format can be simply 2, 3, 4, 4, 3, minus 2. Yes or no? Will this work? Will this input format work? Don't try to have an input like 2x plus 3y is equal to 4, 4x plus 3y is equal to minus 2. When you try to give input like this, then it becomes a mess. So this is the input format which you should try to give. Okay. So the problem is, this is the thing that I want you to understand, that there is a real world problem that is there. How do you kind of represent that problem in your computer? Okay. What is the storage structure that you use to represent that the real world problem? Okay. And how do you input it? Okay. How do you provide, what is the input format, what is the output format, what is the internal storage structure? These are the questions that you need to ask when you are trying to solve problems. Are you all with me here so far? All good? Okay, I would like to stop here. So on in the next class, storage is 2D array. You can use a 2D array to store it. Okay. In the next class, perhaps we will write few programs using recursion. Recursion is a very interesting idea. So maybe Thursday and Saturday class is about recursion. Assignment 2 is not released on OJ. It looks like that. So assignment 2 we will release, and also we will assignment 3 will be released. Yeah. So quiz we will see. I will have the quiz sometime, maybe this Friday or. Friday is New Year. Huh? No, na? Okay. That's all from my side today. I hope you're all enjoying the course so far, not getting overwhelmed. Well, more new set of problems will come. They'll be fun, hopefully. And see you in the next class. Bye, everyone. Merry Christmas, happy holidays, and everything. See you.